Hello, this is Ying. Today John and I will present together about measuring the variability of chain letter reserve estimates. During the insurance rate making class, we have learned how to use chain letter method to estimate the reserve. But how accurate is the result of this forecast? In this paper, Thomas Mack introduced a method to figure out the confidence interval for the outstanding claim reserve and for the ultimate claims reserve using the standard error for the standard deviation of the outstanding claims reserve. So here's our goal to estimate ultimate claims amount CII. So we show the core formula here to calculate the estimate value of CII. We do it by multiply CI, I plus 1 minus I, by all other H to H factors. And we are using same H to H factors FK for different accident years. And the only C here is the most recent observed value. We treat it as the basis for the projection to the ultimate amount. Here is the formula of how it is calculated for the H to H factors. So we know that it is very popular to use chain letter method in insurance industry because it's pretty simple without any assumption. But it is proved to be wrong in this article. We still need assumptions for this method. So let's see what assumptions are needed. The first one is the expectation value of CIK plus 1. It is calculated by CIK multiple FK. And actually this is a conditional expectation with knowing all other historical data. And this assumption is based on that same H to H factor should be used for different accident years and also uses only the most recent observed value CI, I plus 1 minus 1 as basis for projection ignoring all other data. These two aspects are consistent with our core formula we just talked, which means that the first assumption is wrong and cannot be taken away. Assumption 2 here is talking about that different accident years should be independent with each other. It's true because if we treat them as dependent with each other, we still need to consider the coefficient between year and we may introduce more complicated calculation which may lower the efficiency. However, it doesn't improve any accuracy of the forecast. So we need to regard them as independent. This assumption is met for every runoff triangle, so it is also one assumption that cannot be taken. The last one here is to calculate the variance. However, this one may not as hard as other two assumptions because it needs further checks to see whether it is met for every runoff, and it cannot be used as a priori assumption. However, our goal is to calculate the standard error of the estimated ultimate claims amount using assumption 1 and 2 on the independence of the accident year, and the last one we can calculate our goal standard error of estimated ultimate claims amount, which we can see how accurate is our forecast. So next, John will talk about these three assumptions furthermore.
Okay, so I'm going to be touching on some of the details of the paper. I'll first go a little bit more into the details surrounding the three assumptions that we have previously mentioned. Then I'll very quickly go through Chapter 4 of the paper, which will establish how we find the squared standard error of our reserve. So assumptions 1 and 2 are very similar to each other in that they're both implicitly derived from how we calculate our ultimate claims amount. Assumption 1 says that given that we know the claims amount made up to development year K, our estimated claims amount for year K plus 1 is equal to our claims amount in year K times our H to H factor. So, for example, that means if we're calculating this claims amount in year K plus 1, it would depend on the claim amount made in this year and our H to H factor. It wouldn't depend on the claims made up to that point. Assumption 2 says that the claims amount in one accident year are independent from the claims made in another accident year. So, for example, the claims made in this row are independent from the claims made in this row, and this row, and this row. Assumption 3 has a little bit of a different proof than the last two assumptions. Assumption 3 is the variance for our claims amount in year K plus 1, given that we know the claims made up to that point, is equal to our claims amount in year K times the constant alpha K squared. TMAC gets this equation from first calculating H to H using a different method than what we usually use. We usually use the weighted average method. Here he uses the arithmetic average method, which he finds that the H to H factor is being multiplied by a weight, and the weight will be inversely proportional to our variance. When relating that back to the typical way we calculate H to H, our weight is equivalent to our claim amount in year K. So he gets this formula, and using the rules in variance, he gets back to the formula in assumption 3. So chapter 4 starts off with a bunch of equations that lead up to the mean squared error of our ultimate claims amount. He then equates the mean squared error of our ultimate claims amount to the mean squared error of our reserve by saying that they're both equal to the same thing, so they're equal to each other. So by having the mean squared error of our ultimate claims amount, we have the mean squared error of our reserve, and we also have the standard error of both. Chapter 4 then concludes by choosing which distribution would be best to measure our reserve. It determines that log normal is best and adapts the log normal formulas to the mean and variance of our reserve, and gives us the formula for the squared standard error of the reserve. Next, I will move on to the example given in Chapter 6 of the paper. The data for the following example is taken from the Historical Loss Development Study published by the Reinsurance Association of America. The table is cumulative, so we're used to using that. And it then calculates the age to age FKs, with FK1 being how we normally calculate it with Formula 2, FK0 being from Formula 12, which is the FK we get when we estimate it from a regression, and FK2 being from Formula 13, which is the arithmetic average found using weight 1 divided by claim amount in year K squared. The paper then plots the different claim amount in year K plus 1 against the claims amount in year K, all the way to ultimate. I've posted 3 of the 8 graphs with their weighted residuals below them. And we can see as time goes on, our estimates get closer and closer to the age to age factor. And for these graphs, we're using the FK1 method, which is the typical method. The paper doesn't graph the FK0 and FK2 method, but it does look at the weighted residuals and determines that it's close enough to the FK1 method that we can proceed using our FK1 method of calculating age to age. So now that we've decided which FK to use, we can now calculate our reserve. We use Formula 8 to calculate the alpha k squared and Formula 11 to calculate the standard error for our reserve. And because the total of our standard errors are above 50%, we should use the log normal distribution when calculating our confidence interval. Using the methods in Chapter 4, we find the upper 90th percentile bound for the confidence interval is 86,298. We then use the equation derived from Chapter 4, and we find that t is equal to 1.13. So this is the t we need for all of our upper confidence limit reserves to be equal to 86,298. So using that t, we can calculate the individual upper confidence limits for our reserves. We calculate the lower confidence limits in a similar way, and that finally gives us our confidence interval for our reserves. So in conclusion, using the three assumptions that TMAC provides and checking to see if they hold for the triangle we're using, we can estimate our reserve using the chain ladder method, but more importantly, we can construct a confidence interval to see how accurate our estimate is. Thanks for watching.